Light and water, the source of life on Earth. There it is, coming from stars in the universe, like our Sun, traveling at a speed of 300,000 kilometers per second. It's there, and we take it for granted. The Sun, our closest star and our main source of light, rises and sets every day. Day turns into night, and night turns into day. But is it that simple? When you gaze at the sky, you marvel at its intensity. Who knows how many stars there are? This question has fascinated scientists and philosophers and dreamers throughout the ages. One of them was Sir Frederick William Herschel, born in 1738 in Hanover, Germany. Herschel became well known as both an astronomer and a musician. He moved to England in 1757. Herschel is famous for his discovery of the planet Uranus in 1781, the first new planet discovered in the modern era. But Herschel made another dramatic discovery in 1800. He wanted to know how much heat passed through the different colored filters he used to observe sunlight. He noted that filters of different colors seemed to pass different amounts of heat. Herschel thought that the colors themselves might be of varying temperatures, so he devised a clever experiment to investigate his hypothesis. He directed sunlight through a glass prism to create a spectrum, and then measured the temperature of each color. Herschel used 3 thermometers with blackened bulbs for each color of the spectrum. As he measured the individual temperatures of the violet, blue, green, yellow, orange, and red light, he noticed that all of the colors had temperatures higher than the controls. Moreover, he found that the temperatures of the colors increased from the violet to the red part of the spectrum. After noticing this pattern, Herschel decided to measure the temperature just beyond the red portion of the spectrum, in a region where no sunlight was visible. To his surprise, he found that this region had the highest temperature of all. Herschel's experiment was important because it marked the first time that someone demonstrated that there were types of light that we cannot see with our eyes. What Herschel had discovered was a form of light beyond red light, now known as infrared radiation. Our eyes are detectors that are designed to detect this visible light. There are other forms of light that we cannot see, as Herschel had discovered. Few animals can see infrared. However, rattlesnakes and other pit vipers have 2 small organs or pits between their eyes and nostrils that detect infrared radiation. Hence, even in the dark, they can accurately strike at warm-blooded prey. The human eye can only see a very small part of the electromagnetic spectrum. At one end of the spectrum, we cannot see gamma rays, ultraviolet light, and X-rays, while at the other end, our eyes cannot see infrared, microwaves, or radio waves. Infrared radiation lies between the visible and microwave portions of the electromagnetic spectrum. The difference between infrared and visible light is the wavelength. Infrared has a longer wavelength than what we can see with our eyes. We can illustrate this in another way too, using Max Planck's law of radiation, formulated in 1900. It's an equation that produces a curve which illustrates that the warmer a body is, the greater its emission at each wavelength, and the shorter the wavelength at which emissions peak. It seems complicated, but it isn't. This is the curve at 37 degrees Celsius, the normal body temperature of a human being. Maximum radiation is emitted at about 9.3 micrometers, and we can only see this radiation with an infrared camera. If the temperature rises to, let's say, 300 degrees Celsius, the temperature of a soldering iron, the peak of radiation moves to about 5 micrometers. We still need an infrared camera to see this. Suppose the temperature rises to 5,500 degrees Celsius, the temperature of the Sun. Then the peak of radiation is 0.5 micrometers, and this is right in the part of the spectrum that we can see with our eyes. The primary source of infrared radiation is heat or thermal radiation. Any object that has a temperature above absolute zero emits radiation in the infrared region. Even objects that we think of as being very cold, such as ice cubes, emit infrared radiation. We experience infrared radiation every day. The heat we feel from sunlight, a fire, or a radiator is infrared. And although our eyes can't see it, the nerves in our skin can feel it as heat. The warmer the object, the more infrared radiation it emits. An infrared camera, also called thermal imaging camera, will measure the amount of infrared radiation falling on its detector. Through special calibration, some thermal imaging cameras are able to measure the temperature of the object. Thermal imaging is not the same as using night vision goggles. No, night vision goggles amplify small amounts of visible light so that objects can be seen at night. They only work if at least some light, like moonlight or starlight, is present. Thermal imaging works by detecting the heat energy being radiated and needs no light at all. The first thermal imaging camera for military purposes was developed in 1958 by AGA Bofors in Sweden. In 1965, the first unit for industrial use was sold. In the same year, a commercial scanner was brought to market too. Today, FLIR Systems develops and markets the most sophisticated thermal imaging cameras with uncooled and cooled detectors. But how does a thermal imaging camera work? Although a thermal imaging camera looks a lot like a normal video camera, it's far from the same thing. Glass does not transmit infrared radiation well, and so the lenses of an infrared camera are made of germanium. This expensive metal is a good transmitter of infrared radiation. Infrared energy coming from an object is focused by the optics onto an infrared detector. The detector sends the information to sensor electronics to process the image. The electronics translate the data coming from the detector into an image that can be viewed in the viewfinder or on a standard video monitor or LCD screen. Infrared thermography is the art of transforming an infrared image into a radiometric one, which allows temperature values to be read from the image. To read correct temperatures, one important thing needs to be taken into account, and that's a factor known as emissivity. Emissivity is the efficiency with which an object emits infrared radiation. This is highly dependent on material properties. It's important that you set the camera to the correct emissivity, or you'll measure the wrong temperatures. If we look at a man and bring the emissivity down, the temperatures we measure will rise drastically. Not only is this true for human beings, but it's true for other materials too. It's extremely important to set the camera to the correct emissivity. FLIR Systems thermal imaging cameras have predefined emissivity settings for lots of materials, and the rest can be found in an emissivity table. More than 200 years after Herschel's discovery, thermal imaging cameras have become compact and easy to use. Cameras which are engineered and designed by FLIR Systems are based on the most advanced technology, both in terms of hardware and software, and have contributed to the positioning of FLIR Systems as the world leader in thermal imaging systems. Systems that are used in the widest variety of commercial, industrial, and government applications. Recent developments in detector technology have led to many useful applications using infrared radiation. Predictive maintenance, machine vision, and research and development. They all benefit from the advantages of thermal imaging. Thermal imaging is used to detect heat loss in buildings, to test for stress and faults in mechanical and electrical systems, and to monitor pollution. In firefighting, thermal imaging cameras are used to locate people caught in heavy smoke and for detecting hotspots in forest fires. And there are lots of night vision applications that don't require temperature measurement as well. Security and surveillance, maritime, automotive, law enforcement, and many more. They all benefit from the power of thermal imaging. It's thanks to William Herschel's amazing discovery and the never-ending commitment of FLIR Systems to develop the best thermal imaging cameras on the market that we are able to see things in a different light. Light, for example,